Counting off. Cool. Yep. Hi everyone and welcome to this video. We're going to do angle of inclination today on this part. We're then going to move that on to angle of elevation and angle of depression, more practical type questions. So when we're talking about angle of inclination, the definition around angle of inclination is that it's the angle that a line makes with the positive x-axis. So what that really means is draw any line, start on the x-axis and make an angle till you get round to the line. This one's not so bad. You can probably think, oh well, that's okay, but on this one where the line's the other way, you still start on the positive x-axis or towards the positive direction and come all the way around. That then means that no angle of inclination is going to be greater than 180 degrees. Because think about this line here. If I keep moving this line around, I get to 90, all the way around I get to 180. When I would start to go a little bit further, I actually create a new angle of inclination there. Okay? So I'll start with a 0, it'll get bigger to 90, round to 180, and then when I go to 181, it's actually a 1 degree angle of inclination. So I never actually get greater than 180 degrees for an angle of inclination. So these two here describe, or give you an example of the two of them, and it's really just a matter of measuring it or figuring it out in some way. Questions like this might give you the angle, and then ask you to determine the gradient of that line. Well, we can do that as well, so long as these ones come up to certain angles. If you remember, we did exact values for trig. So if you've got 30, 45 or 60 degrees, or some combination of that in the second quadrant, then we'd be able to figure out the gradient. Let's put an example in here. Let's put 30 degrees in here. If I've got 30 degrees in there, you can see this triangle here. I've really just created a triangle in there, and it doesn't really matter how big the triangle is. The only key thing is the 30 degree angle. So that means 30 degrees would be here, and because I would drop this down so it hits at 90 degrees, that forms me a right angle triangle. Now if you remember with your right angle triangles and your exact values of trig, I could say that the sine of 30 degrees is equal to the opposite over the hypotenuse. I could also say the cos is adjacent over hypotenuse. I could also say tan is opposite over adjacent. So I've got three ratios that I can really use. Now I'm going to use the tan one. And if you remember that tan of 30 degrees, well, sine of 30 degrees is normally an easy one to remember. So start there. If you can put to memory sine of 30 degrees equals a half, that's often going to help you out. From here, opposite over hypotenuse. That's what sine is. So I'd go 1 and 2. Now then we'd do a bit of Pythagoras, and you might now be remembering what the tan of 30 degrees is. If we do a bit of Pythagoras, this is going to be 4. I've already got 1 here, so I need another 3. So this would have to be the square root of 3 down here. Alright, let's check another ratio. Cos of 30 is adjacent over hypotenuse. I remember that, square root of 3 over 2. That makes sense. Now that means the tan is opposite over adjacent, so this is going to be equal to 1 over the square root of 3. Now the idea of doing tan there is important because if I wanted to know the gradient of this line, gradient is rise over run, isn't it? So isn't the rise just this dimension there? And isn't the run just this dimension here? So isn't the tan really equal to the rise over the run? And hence the tan of the angle that I have here is really the gradient as well. Because tan is opposite over adjacent. Well, the opposite is the rise, and the adjacent is the run. So my gradient for this line here is actually going to be exactly the same as what I just worked out over here. 1 over square root of 3. Now the same thing applies over here, but we've got to be a little more careful. I've got this angle over here, and I'm actually going to say that the question gave us this angle here, 135. So if it gave us that angle, the angle of inclination of 135, because I know that this is a straight line, over here has to be 45 degrees. So if I've got 45 degrees there, this triangle that I pulled out down here, I might just make that a little bit bigger. The size doesn't matter, but just so you can see. then 45 degrees is going to be there. Again, remember some of our ratios. If I've got 45 degrees, I reckon that this is going to be 1, 1 and square root of 2. So if I work out the tan of this, tan is opposite over adjacent. So the tan of 45 is going to be 1. Or let's put 1 over 1, so we bring in the rise over run idea. So therefore, the tan of 45 is 1 over 1, but I've got to remember that this, because of the angle of the line, is actually going down. So this is really negative 1 on the rise, 1 on the run. So if I add this in and do my gradient, that would be negative 1 over 1, giving me negative 1 as the gradient. So I'm still using the tan idea, but I've got to be aware it's going downhill. So this is actually going to be a negative 1 on the rise part, but still positive 1 on the run part. So I've got a gradient of negative 1 for this line, and that seems to fit pretty well. Now an extra step to this that might not be needed in your course is to look at the angle of inclination and talk about angles of elevation and angles of depression. If this is us standing down here and we want to look at the top of the building here, then our line of sight is going to be that one there. And hopefully you can see that if I dash the line from my eye height to there, I can form a right angle triangle. So if the question gives me some dimensions here, let's say I'm 20 metres away from the building, and let's say that I'm 1.8 metres high, so my eye level is 1.8 metres, and then let's say that you figured out as you were looking up, you figured it was a 30-degree angle there. Now again, I'm choosing those angles so we've got our exact values, but in a calculator section you could have any values in there. So let's drag out that triangle. The triangle is going to look like this. 20 is going to be there, 30 degrees is going to be there. Now I'm not worried about this 1.8 at the moment. This is not critical at the moment. Because I want to know this distance here, that's kind of part of the building height, I want to go tan of this is opposite over adjacent. So the tan of 30 degrees is equal to, I'm going to call this h over 20. Do a bit of rearrangement. H is going to equal, multiply the 20 up here. 20 multiplied by the tan of 30 degrees. Well, that's handy. We had that over here. 1 over square root of 3. So therefore, as an exact value, running out of room here, 20 over square root of 3 metres would be the height of this part of it. And if I wanted to know the height of the building, I'd just add the 1.8 onto that, get a decimal equivalent, and I'd be fine. Bit of estimation here, square root of 3 is 1.7. So if I was to divide that by 2, I'd get 10. But this is only 1.7, so it's going to be maybe 13, 14, something like that. Add the 1.8 on, maybe it's 15 or 18. Something around that figure anyway. Have a good estimation ability is really handy. The other way that we can do this sort of question is angles of depression. We're flying along in a plane, we spot the boat that's in trouble down in the water, and someone figures out that they are looking down at an angle of depression of, I'll say 45 degrees for this one, use a different number. And the pilot says, oh look, we're travelling at 1,400 feet. Planes generally travel in terms of feet. So the pilot reads off his dial and says, we've got 1,400 feet. So you can probably see now in here, there's another triangle. Grab that one out, what have we got? We've got right angle here, we've got 1,400 there, we've got 45 there. And what we'd be figuring out is how far are we away from the boat? Because if there's another boat maybe over here somewhere that's going to go and try and save them, we need to be able to figure out where that boat is exactly. We do a bit of a calculation here. Tan of 45 is opposite over adjacent. We'd use those numbers, come out with our tan value, and we'd be able to say to the rescue boat, this is where you need to go. This one as well, I've simplified it to a two-dimensional setup, but of course you could add in a three-dimensional aspect to that. You're looking down at a particular angle, but you're also maybe looking at a particular compass bearing north, south, east, west to then direct the boat on. That's not really important. What's important is really this idea of pulling out the triangle, using our trig knowledge in right angle triangles to find the distance that we want. Hope this one helped. Thank you.